Today's episode is sponsored by SONUSFABER. Fine, handcrafted loudspeakers designed and manufactured in Vicenza, Italy. With over 35 years of advanced technological research and development, our elegant designs will allow you to experience an emotional connection with your music like never before. Discover your local dealer at SONUSFABER.com. Today's episode is also brought to you by QOBUZ, lossless and high-res streaming and downloads. 50 million tracks in all genres in the best possible quality. QOBUZ supports the audio industry and appreciates the needs of discerning audiophiles. Try it for free now at QOBUZdotCOM. That's QOBUZ.com. You have arrived at Season 4, Episode 2, our interview with Rob Watts. Rob Watts is a very elusive character to get a hold of. I've actually seen him many times at CES, giving amazing presentations, filled rife with information. He's a smart man, digitally savvy as all can do. And frankly, a very knowledgeable individual who kind of is one of those inspiring designers that is seeking perfection, looking to produce the best quality sound out there, which is totally awesome. And he makes some really great stuff. He's super into it. He's not just, out there to make a quick buck and then get out of the industry. He brings a wealth of knowledge. He, has seen a lot of success lately with everything he's done for one of the companies that he works for called Chord Electronics out of England. That company's had great success with the Chord Mojo and then the Poly and a whole wealth of other products, including their Dave DAC, which is a more of a high-end product. That turned out really well. That's what I saw at CES a couple of years ago. We actually kick off the show with a conversation about his views on some analog things, but don't worry, we dive into all of his digital kind of ideas very quick after that. The one thing I got from this interview is that he is one of these designers that really has a great balance when it comes to listening and also design and technical aspects. So he just crushes it in terms of how he listens and incorporates that into the final product. Also, I just want to remind you guys that ZUAUDIO, a sponsor of this show, has their big Omen Dirty Weekend sale coming up. The Omen was one of my first loudspeakers when I got into this hobby, and I thought it was just an amazing speaker for a kind of an entry-level price. And a few times a year, they actually have these type of sales where they'll put the Omen on a special discount. It starts around $1,000. But the supply is usually very short, so you gotta act quick because they sell out in sometimes just hours or minutes even, I'm not really sure, but they sell out pretty quick. And this one is coming up July 1st at noon, I believe you can start to place your orders. So if you're interested in a cool looking and cool sounding loudspeaker for relatively cheap, you can check out their page at ZUAUDIO.com. Right on the homepage, there's a link to take you to the sale landing page. So on with the show. Here we go. Digital Master Rob Watts. What's your title?
Interesting question. Because from a commercial point of view, it would be better if I was a Chord employee and I'm Chord, but I'm not Chord.
Okay.
So I'm actually an independent design consultant, and in the past I've worked with major silicon companies, worked with one other small high-end company as well. But I've worked with Chord for a very long time, since 1997, designing their digital products. From about 2001, that's when the semiconductor design really kicked in. So for about 14 years, most of my activity was semiconductor design. So I was spending a lot of time coming over to the US and seeing the foundries and doing work with my clients. I still kept things going with Chord. It was very much part-time activity and designing and developing products that I wanted. So it was more of a fun activity. It wasn't commercial. And then with Hugo, everything completely changed. Chord's business took off, and I found myself spending more and more time doing high-end design work, and that's the thing I really like to do.
Why is that?
Well, there's issues with semiconductor work, lots of different issues. One problem is that it is not about creating the best possible performing device. It's about making it good enough. And that term good enough grated with me constantly. There's also issues, which actually turn out to be very interesting. There is issues with silicon design work that you don't have when you're designing FPGA discrete DACs. You've got issues of substrate noise. You've got problems with the innate nature of silicon, such as resistors being nonlinear and capacitors being nonlinear, and you have to deal with all those issues. Now, they're technically very interesting and quite challenging, but it does mean that you've got a limited performance. The other big major stumbling block or issue from my point of view is you're very much limited on cost. So, for example, was one project I was working on, we were 5 cents too expensive, so they were going to cancel the whole caboodle, and millions of dollars had been spent, and so we just had to redesign it. And 9 months later, we just got a die shrinkage, and everything was hunky-dory, and it went into production. But it illustrates the kind of pressure that you're under. It's high volume, it's not high end.
I once had a friend who designed laptop bags in this thing, and I was like, that sounds, just generally speaking, I was like, that sounds really fun. You just get to be creative and do these 3-dimensional design elements.
Sure.
And she was like, it is not fun. The number one thing I do is cost.
Yeah.
So there's not. I'm just saying that it sucks a little bit of not only the creativity but the fun out of it when the main concern isn't being creative. It's making something that will sell.
That's good enough.
Grinded so hard against cost that that's everything. All the thought about it is ground away into that kind of idea. Yeah.
So with Chord, it went from a case of being basically a hobby, doing things for the fun of it, not a commercial involvement, until when the royalties started to kick in because of the volume of the products that were being sold became pretty substantial, very substantial.
Right.
And then it meant I could just focus all my activity on high-end audio, and that's the thing I really want to do and really enjoy doing. So it's been really cool.
I love that story.
Yeah,
that's like that's the kind of thing that makes me happy. I can't explain. I've done over 70 of these interviews, but that's wonderful. I'm glad that you've had that kind of experience. To me, it's almost like the equivalent of a rock and roll story.
Yeah,
right? You get to do something that you love and able to sustain yourself doing near the exact thing that you want to do.
Yeah.
It's wonderful.
Yeah.
I've seen your presentations at CES.
Okay.
Familiar with some of your work. I would like to kind of kick off this podcast, though, with a general questions, and we'll get into the weeds and the technical details.
Cool.
But one of the things I think that you could help our listeners out most in is what are some things that people can listen for in a great DAC? And that can be not just the way it sounds, but are there specific elements of design that make the most difference, or what are some things? Because not everybody can afford the Dave.
Yeah.
Right.
But then you get mini Dave with a Mojo.
Right.
And if you can afford a smartphone, you can afford a Mojo. In one sense, you can answer this very, very simply. I mean, what is the purpose of a DAC? And it's to enjoy music on. So if you find yourself getting more emotional with your music and it's making you happier, then it wins. And it's as simple as that. And in my sense, being able to get emotionally involved with the music, when you objectively analyze what do you need a product to do in order for you to get emotional, then actually it comes down to, in one sense, a very simple thing, and in another sense, a very complicated thing. And the simple thing is we've got to make it easy for the brain to decode what the ears are actually listening to. So when we think about music and the listening experience, it's very easy to take it totally for granted. The brain is doing an extremely complicated job when it's processing information. So the illusion of having separate entities, separate different sounds, separate different instruments, placed in a soundstage, all of that is completely created by the brain. And it's a complete illusion. We tend to take it for granted. We think, well, I can hear something there, that's something there. No. It's data from the ears. The brain is processing that information. It's separating individual sounds out. We have no idea how the brain manages to do that. Putting placement tags, calculate where the depth actually is, and the depth perception is incredible. You can be listening in a concert hall, let's say it's a 60-foot depth concert hall. You can easily distinguish between a violin and a guitarist that's separated by one row, and you can shut your eyes, you can perceive that 3 feet different in depth on a 60-foot hall. That is phenomenal accuracy. Mm-hmm. And get a computer program to say, where is this instrument? Get it to separate individual instruments out. It can't do that. Where is that instrument placed in space? It can't do that. And we don't know how the brain does it. And not only that, I wouldn't know how to go to approach to start to answer the question, how do we separate individual sounds out? How do we put placement on those individual entities? So what I found is that if you can make it easier for the brain to do that job, then it becomes more emotional and more engaging. Because if you're having to struggle to understand where instruments are, how they're separated, you get tired, you get listening fatigue. And also the brain is busy doing things, trying to make sense of what's going on. What the brain should be doing is understanding the music conceptually and getting engaged and emotional with the music. And you can only do that if you're not being busy and not being worked hard. So the real question is, how do we, as an engineer, make it so that it's easy for the brain, the errors that are inside the product doesn't interfere with the brain's processing. And that's where it gets complicated and very difficult, because there are a huge amount of effects that can happen that can degrade the abilities for the brain to make sense of what's going on. So the short answer is enjoy the music. The longer answer is you've got to look at lots of different parameters.
What role do you think distortion plays in that idea of making sense of what we perceive? Is it possible, in your mind, that we detect a certain amounts of distortion in our natural environment, and that's why analog or tube sound, some people will say, sounds more real to them?
Oh, you can. There's some tracks on the internet where people have put some processes in that add second harmonic distortion, and you can see the processed track and the unprocessed track. I don't like the sound of the processed track because things have got a sameness quality about them, and it sounds compressed. It sounds a little warmer and heavier, and I could see someone wanting to process an individual instrument that way, but to process all of your instruments, all that happens is that everything gets muddled and confused. I think the issue with some designers, for example, are trying to create a particular type of sound. So they may go for a hard, analytical, supposedly transparent sound, artificial sense of detail. And then on the other side, you've got the designers that go for a soft, warm, smooth sound. Personally, I prefer a soft, smooth, warm sound because, it's easier to get engaged with something that's warm. But what we actually need is hard, fast, aggressive, and at the same time, warm, smooth, and refined. Because when you listen to live music, you listen to a saxophone, rich and dark. You listen to a trumpet that's very close to you, that can sound hard and really aggressive. And we need an audio system to be able to play simultaneously all these variations. One of the key parameters that I look at when I'm assessing a product or a process or a design, when I'm assessing that, is the amount of variations that is occurring when I'm doing the listening. So, can we hear variations in timbre? Can we hear variations in tempo? Can we hear pitch? Can we follow the tune? Placement of instruments? How much depth can we get? All of these things, the variations, looking at things in terms of making the music more varied, is a good way of assessing whether you're actually making a product more transparent or not. Because we're all using recordings. We don't know where those recordings came from. We don't know how they were recorded. We don't know the original event. We weren't there. So how can you make an assessment on a product as to whether it's more transparent or not when we don't know what the hell we're listening to? And the way of solving that problem is to say, okay, if I'm listening to something and it's more varied in all these different factors, then we know we're making it more transparent because it's being more expressive.
So what you're alluding to is that if there's a general idea of a smear, where things like a painting, but the defined lines get kind of smeared, that is this. It's a lack of variability.
Yes.
In terms of color, in
Yes.
like a visual sense, or the hard lines around the edge of an object.
Exactly. And when you see an object that's been painted slightly out of focus, you want to be able to perceive that. When you see an object that is sharp and well defined, you want to be able to see that as well. And most designers will make everything soft and out of focus, or they will make everything sharp and in focus and artificially sharp for when things are supposed to be out of focus. So it's about trying to make what your experience more expressive, more variation in the program material.
To kind of circle back to my original question, in your opinion, what do tubes do to that scenario?
Well, tubes are quite interesting because one of the parameters that I look for is a technical issue of noise floor modulation. And noise floor modulation is something you can easily measure, but it's something that also has a very substantial change to the sound quality. So with noise floor modulation, you have a small sound, a small level, and you have a fixed level of amount of noise. But as the sound level goes up, then the noise floor goes up, and the noise pumps up and down with the signal. That makes warm-sounding instruments sound bright. So it's a bit like if you've got a saxophone, and you've got the sound of the saxophone. If you've got a noise that is pumping up and down with the saxophone, the brain cannot separate the sound of the saxophone against the sound of the white noise. And if it's a white noise, it's bright, and that makes the saxophone sound brighter. So the benefit of valves is that you use local feedback around the valve. It's got a high internal overload margin, and its RF linearity is pretty good. Now, the problem with noise floor modulation is down to RF noise. You get random RF noise getting into your electronics. It then mixes with the analog signal. You get intermodulation distortion. The intermodulation distortion product is random noise. So this is your mechanism for creating noise floor modulation. So the benefits of valves or tubes is that innately it can suffer less from noise floor modulation. So that's a benefit. So things sound naturally warmer and smoother. The downside, of course, is that it creates more distortion. So you can have nice amounts of second harmonic, which also makes it sound warmer. But there are plenty of valve companies that I know of that actually do have quite low levels of harmonic distortion. It is possible to engineer a valve that way. The other issue that valve amplifiers have got is that they tend to have rather large amounts of output impedance because there's a big transformer in the way. That means the damping factor is poorer. Poorer damping factor means that you get more output at low frequencies, which makes it sound warmer again. So with tube equipment, there's definitely some things that artificially make it sound softer and warmer, but there's also some things that are innately better or innately easier because of this issue of noise floor modulation. That's not to say that with semiconductors, you've got an innate disadvantage. You can make semiconductor designs work so there's no noise floor modulation, but you have to be very careful about your RF noise. You have to be careful about your open loop nonlinearity. You have to be careful about how things are laid out and how things are decoupled and that kind of thing. So it's perfectly possible to make bipolars or MOSFETs not to suffer with noise floor modulation. It's just a little bit harder, and you've got to work at it, and you've got to know what you're doing.
Does any of that relate in any way to a typical audiophile's obsession with Class A topology?
Class A is an interesting one. And the reason why Class A is important is because of when you switch to Class B mode, you get crossover distortion. If you analyze that, you'll get harmonic distortion at a fixed level going up to infinite frequencies. And that's very nasty because there's a lot of higher order harmonics and it causes immense problems because it's so audible. But it's perfectly possible to have a Class AB output stage and to completely eliminate crossover distortion. So one of the things that I do on Hugo 2, TT2 and the Dave is I've got a second order amplification system. What happens is there's one amplifier that is linearizing the output stage, and that's inside the global feedback loop of the whole amplifier. So you've got kind of a super linear output stage because of this feedback amplifier inside to linearize the output stage, and then you've got the conventional amplification. So still one single global feedback, so the signal is going through one set of feedback resistors, but inside it's very, very linear. The benefit of that approach is that you completely eliminate crossover distortion. And I can see this on the plots that I've published for TT2, in that if you use a 20 hertz signal, above 3 kilohertz, there's no distortion whatsoever, and that's TT2 driving into an 8 ohm load at 12 watts worth of output. So there's absolutely no harmonic distortion at all. And this is with a noise floor of minus 180 dB. So, it's possible to eliminate that issue. But of course, the trouble with audiophiles is that they tend to think simplistically. Class A must be better than Class B. It's not quite as simple as that. What we need is an output stage that's linear. We don't need a Class A or a Class B output stage. We need something that works. And my message is a little bit more complicated, but yes, Class A certainly is better than Class B because of this issue of crossover distortion.
And Class D?
Oh, don't go on about Class D.
I've talked to a lot of amplifier designers. Are things changing though? Right now, I can just tell you that there are certain people that are highly impressed with things that are in research stage, but nothing quite that has come to market yet. But there is a buzz and excitement about it. Do you have any exploration into that, or is it just a hands-off deal for you?
Class D has got innate problems. The issue of noise floor modulation is a major issue with Class D, and certainly for the lower quality Class D, it's a huge problem. I have actually worked on Class D amplifiers and designed Class D topologies before. Class D with feedback, and gotten extremely good measured performance, no noise floor modulation. So it's possible to solve those issues. The downside to Class D is the transient reconstruction. So what the problem we have here is that you've got a switching output stage. And it's a PWM output stage, generally speaking. So it's pulse width modulation. Right. What that means is that as your signal gets larger, your effective delay changes because the signal is changing. It's a PWM. And it means that your transient timing information is being modulated by the signal itself. Transient timing reconstruction is incredibly important. And I've always known it's been important because we know from studies of the interaural delay and the way the brain works that we can perceive down to 4 microseconds worth of delay between the left and the right ear. But one of the very interesting things I did with the Dave project was that my interpolation filters within Dave originally worked up to 16 FS, so 768 kilohertz. And then above 768 kilohertz to 12 megahertz, I was using a 3-stage filter. And in fact, that filter goes up to 104 megahertz. So it's a 3-stage filter. You got rid of all the external noise from the oversampling and from the images that's within sampled audio. And it worked very well from a technical point of view. But then I decided, okay, let's have a bit of fun. Let's try replacing this filter, part of this filter, with a WTA filter. And let's see how much extra resolution do we need. Because a WTA filter at that stage, it was producing an output every 1.6 microseconds. Mm-hmm. But what if we can hear, what limit do we need to do in order to refine the timing and to make the reconstruction more accurate to the original analog signal? What level do we need to do? And it's all very well saying 1.6 is better than 4 microseconds, but until you do a listening test, until you actually try it, you don't know because you're making an assumption that it's good enough. So I tried this one that ran to 88 nanoseconds. So you had another WTA filter replacing the conventional IR type filter with the WTA filter, and you could hear an immediate difference. And the way you perceived the difference was on the starting and stopping of notes. So, which is a little bit different to how WT algorithms normally change the sound quality because other things happen. But it's being able to perceive, for example, a piano when you first hit the keys, the way the pianist hits the keys changes the timbre, changes everything. And being able to perceive that very first snap of sound, that's really, really important. Mm-hmm. Changing this filter and dropping this filter and improving the resolution to 88 nanoseconds dramatically improved that perception, that ability. Class D, there's no way you can switch at 12 megahertz. Okay. That's never going to happen. The Class D amps that I designed were running at 800 kilohertz. And some of them would run at 1.6 megahertz, so we could run at 1.6 megahertz. But then you're reliant on your inductor and capacitor output filters to recover the timing information, and the distortion that this is generating in terms of timing errors is too important. And so it will never be as good as a linear amplifier if your DAC is reconstructing the timing information accurately to nanoseconds. And it seems to be that nanoseconds is the issue that we need to in terms of accuracy. So that's a fundamental limit that you're never going to be able to resolve. Now, I'm sure you can get with feedback Class D amplifiers to work correctly. I know I've designed them and they work very well, and you can get audiophile quality performance, but you can't get state-of-the-art because you're limited by this issue. Having said all that, there's been a project that I've been working on for a long time that enables the benefits of Class D in terms of efficiency, but doesn't have a switching output stage. It's a linear output stage. And this I'm testing at the moment, so we hope to have products available in the next year or so when that becomes available. That's going to change things quite radically because we'll have very simple DACs with 2 resistors, 2 capacitors, 1 linear amplifier, but capable of delivering hundreds of watts. So that's quite exciting when that actually happens. And not having huge amounts of power dissipation, but still being Class A. So, and it uses a Class H approach in terms of the power supply.
One of the things that is kind of hamstringing the distribution of like better audio sound, I think, in just a general sense, is size and heat. Like
yes.
There's restrictions on this. The more we can get smaller, better, and obviously in this case faster, the more, I think, expansion we can have into all kinds of stuff. Obviously, size is so important, and not for the audiophile experience, generally speaking, but if in terms of mainstream or even just like the things you could do with a small... I mean, what would you do if you could have that type of big experience from an amplifier standpoint in a very tiny space? I mean, what would you do?
Absolutely. The thing that comes to mind is portable audio. Okay, portable audio, you don't need large amounts of power. But one of the conversations I had at this show yesterday was about the M-scaler. I use my M-scaler on planes, and it's quite a big device. It's sort of 12 inches square kind of size, a couple of kilograms. I use a battery backup to power the device. If I'm flying economy, I just put it in my bag. If I'm flying business class, you can just put it on the shelf and everything's fine. Once you get used to the sound of the M-scaler, you want to hear it all the time. And at the moment, we're stuck because the power dissipation is 12 watts on the FPGA. There's something like 600 DSP cores, 525, I think there is, DSP cores running inside the device. It's always going to be consuming power. So what I want, of course, is an M-scaler that will be the same size as of a Hugo, but we need much, much better FPGAs, and I think we're probably about 10 years away from that. But yes, you're quite right. Being able to, that's a different example of what I'm talking about, but being able to make the power issue being solved with portable electronics is a major, major, major issue. It's something I spend a lot of time on my portable designs, about power efficiency, because you've got a power budget, you've got a battery, you can only dissipate, in the case of Hugo, you can only do 2.5 watts. In the case of Mojo, you can only do 1.7 watts. But there are things you want to do. You want to use that power to improve your sound quality. And there's always plenty of things you can do, like more taps on the FIR filter, more processing, better quality amplification. But these add more to your milliwatt budget. I spend a lot of time with Hugo too, shaving a couple of milliwatts here and milliwatts there so that I can spend that milliwatt budget on improving the performance.
Yeah, I mean, when I think of almost just like the entire landscape of technology, if we can get to a point where power supplies and batteries shrink exponentially as well,
yes,
or just a more limitless sense of supply, I think that the world would change even more dramatically than we've seen. You know, if a battery could be just like a little tiny thing on the board, well, I mean, that would change everything that you do as well, right?
Sure.
If you had a limitless supply of any wattage or any kind of variable that you wanted to do with power, I think that would just be like that portable audio would be a different animal.
Absolutely.
What would you do exactly to make the sound better in that scenario?
Well, the big thing is 1 million taps. And being able to do the M scaler, but even if you had a battery that was small, say the size of your thumb, that could power a 12-watt device for 8 hours, you'd still got the problem of that power. 12 watts in something that's tiny would get very, very hot. So then you've got issues about fans, and the ultimate way.
Can you explain why it would get hot?
Yeah, because Mojo, for example, that's something that is 2.5 inches square in terms of its volume. It's actually got a very limited amount of power dissipation capability, and I can't remember exactly what the numbers were in terms of degrees C per watt, but it's limited. If we went for more than 1.7 watts, it would get very warm. So I think at 1.7 watts, the elevated temperature is about 15 degrees C, from what I remember. When it's charging, it's more like 3 or 4 watts. So it's the charging and playing it at the same time when things get warm. So for something that size, you can comfortably dissipate 3 watts internally. So if we had a battery that was capable of 12 watts, you'd be burning your flesh, unless you installed a fan. There's more to this game than just the battery. It's about how your thermal efficiency is and how you can get the waste heat out of the device.
You brought up harmonics several times.
Yes.
There's even order and odd order harmonics. If you could add just a little of your own personal color to that subject, do even order harmonics sound better than odd order?
You certainly don't want odd order harmonics.
You don't?
You don't, no, because they sound worse than even.
Okay.
Because the ear itself generates quite a lot of second harmonic distortion, and the brain compensates for that. It's cool with even order harmonics, but odd order harmonics it doesn't work so well with. But the curious thing about distortion, there's kind of 2 points I'd like to add. The first one was the experience with Dave. So with Dave, I went through 3 or 4 different prototypes, and the objective was to make it as linear as possible so that we could measure it and we'd have distortion that was so much better than everybody else. And because a lot of my background is with semiconductor companies, they don't care how it sounds. All they care about is the numbers and the measurements. I've always been that way inclined in terms of measurements, as measurements being important, because how do you assess transparency? You can do it through listing tests, but one way is to literally measure things and make sense of the measurements. Anyway, so I had this kind of ambition to make it the most linear DAC available. And I managed to get the first prototype, it was down to about minus 130 dB, which fine. It's very, pretty much state of the art, but it wasn't clearly better than, it was about the same as the best DAC available at that time. So it was just my ambition, and I couldn't figure out where this distortion was coming from. And that was the crazy thing. I just couldn't find out where it was coming from. So built another prototype, assessed one aspect, couldn't get that right, made it slightly better, and then built another prototype and made it slightly better, but I still wasn't getting the fundamental reason why, this thing was creating so much distortion. So I had a breakthrough and I managed to find out where the distortion was coming from, and I got a 30-fold improvement in distortion levels. That's 30 dB. So it went from 130 down to minus 160 dB on the higher order harmonics. So that was a huge change. Wasn't expecting a change in sound quality. It wasn't about sound quality. It was about making this thing as linear as possible. So I did a listening test, and I couldn't believe how much difference it made to the sound. And the funny thing about it was that in the evenings, I normally put my prototypes into the listening room and, watch TV with the kids. And the kids were quite young at that stage. And we used to watch Curious George. You probably don't know because you haven't got children yourself.
I remember from my youth, yes.
Okay. The nice thing about Curious George is...
There's a man with a big hat. And
right?
Yeah.
And the nice thing about Curious George is that they actually have pretty good music on it. And
you're saying it's an animated series now?
Yeah.
It was only a book when I was a kid.
Oh no, this is the TV version of the book. Okay, so and they did a feature film, Curious George, but they did lots and lots, and so he was, it's good fun, and the kids loved it. The music was really good, and I plugged in this change. Didn't tell my son that I'd made a change, and he's turned around and he said, "What have you done? It sounds so different." I thought, yeah, this is a big change. And what it changed was, and this has happened before on a number of occasions, when I've reduced distortion levels, oddly enough, the clarity and the detail resolution gets better. I think it's dangerous to assume that because the ear is only capable of resolving, say, minus 90 dB, and so we don't need to make distortion lower than that level because that's the performance of the ear in terms of listening tests with sine waves. That's a very dangerous assumption because it's ignoring the brain's processing. So the problem with when you reduce the distortion levels, it's not about the ear, it's about the brain processing that information, and the distortion you've created in your product interfering with the brain's ability to separate sounds out. So it's about perceiving clarity and details and those kind of things. That's nothing to do with simple psychoacoustic tests of hearing with sine waves, which actually gives you quite a crude number in terms of what you need to work towards. So there's that as an issue. Second issue is I had a noise shaper that was creating a lot of distortion at 200 kilohertz. 200 kilohertz to 400 kilohertz. It was a noise shaper FPGA issue, digital domain problem. Fixed it, listened to it. You could hear an immediate difference from changing the distortion characteristics at 200 to 400 kilohertz, which is pretty amazing because we can't hear 200 kilohertz. So how can a 200 kilohertz harmonic distortion be audible? And it's getting back down to this perception of transients again, and transient information being really important from a psychoacoustics, from a perception point of view. And when you have these very higher order harmonics, it changes the timing of transients. And if the distortion is modulating the timing of transients, you can then perceive it. So you can't hear 200 kilohertz, but if a 200 kilohertz component changes the timing of a transient, then you can perceive it, because that's in band.
I had expressed even or odd order harmonics, but you're referring to another term that's high order. Can you just explain what a high order harmonic is?
Higher order harmonics is generally, you think of higher order harmonics as your 10th harmonic and above.
So for the way it's been explained to me is that, if there's an octave, this is 10 octaves above the original note. It's a 10th,
so it's
so that would be very, very high. Yeah. Very high.
So it's 10 times. So a 10th order harmonic will be 10 kilohertz as a well, that's the 9th harmonic. So 11 kilohertz against a 1 kilohertz signal. So when we're looking at 200 kilohertz, then you're looking at the 200th harmonic, which is something that on paper would be inaudible.
So to bring it back down kind of to day-to-day observation, would you say that the limitations of Redbook CD quality sound are the best we'll ever hear? Or is there a place for high-resolution audio? And if so, does high-res audio add anything above and beyond to CD quality sound in the exact same scenario?
Okay. That's... My answer to that is going to be quite complicated because Redbook CD is capable of extraordinarily good sound quality.
Okay.
The benefit of 192 is that you're reducing the timing problem.
Okay.
So your transient errors are reduced. And what actually happens if you double the sample rate, you quarter the area of the size of the timing error. Okay. So you're making the error much smaller innately. You don't have to worry about your interpolation filters so much. But it's only making it by a factor of 4, which is 2 bits. So with the M scaler, what we're managing to do is to reconstruct the timing information to a 16-bit accuracy. Okay. And to do that, you need to have a sync function. It needs to be the same as what's called a sync function to better than 16 bits, which is what happens in the M scaler, so that we can reconstruct the timing information to better than 16 bits. So you're getting back to the original analog signal that was not sampled in the A to D converter to better than 16 bits. What you'll certainly find with that is a 192 kilohertz recording without an M scaler. A 44.1 kilohertz recording would sound better M scaled than a 192 kilohertz recording. So this is where it gets complicated, because with PCM you can recover all your timing information completely perfectly if you do enough processing. And it's doing enough processing, doing how the quality of the interpolation filter that's the important thing. My wish would be that we all recorded at 768 kilohertz, because when you hear a native 768 kilohertz recording, it's a real big change against the difference between a 192 kilohertz and a 48 kilohertz is actually quite subtle. But when you listen to 192 against 768 is a massive change. It makes the whole purpose of the M scaler, not necessary then. I mean, before I latched onto this issue, really profoundly, was with Hugo 1. And in that case, I was then filtering up to 104 megahertz and reconstructing the timing above the 4 microsecond point, which is the previous thing I was working towards. And the thing I really noticed was how much better piano music was, because you could hear the starting and stopping of the notes. And before, I really wasn't that much interested in piano music because it was a kind of blur when you were hearing it. But now you can hear each individual note being played, and it just makes it so much more interesting. And you can hear the pianist's expression in his music because of the way he's playing. That initial attack has got so much character in it. Focusing on the accuracy of these small timing things has got big musical benefits. Yeah.
To me, it's sort of one of those things that's like the treat. And also, unfortunately, something that you don't hear all the time. I think, unfortunately, it's a lot of things have to go right to get to that point where you hear that really convincing attack, right? So that the way it strikes off of the bat and in a fault in any one part of the chain starts to blur that initial line.
That's right.
That's so hard when you get that focus, not in the sense of a stereophonic feel, but the focus on the edge of the leading edge of this thing. Yeah. That it's kind of strange. And that's the thing I listen for when I go from room to room to room at a show. I'm not going to say numbers, but it's not in every room.
Yes.
You know? Rob, thank you so much for coming on the show.
It's been a pleasure.
Thank you for listening to The Occasional Podcast Season 4. The Occasional Podcast is a production of the Part-Time Audiophile Network, which includes PartTimeAudiophile.com, The Occasional Magazine, the PTA newsletter, and AudioHead.com. You can stay in touch with us on Twitter, Facebook, Instagram, and YouTube. The Occasional Podcast is produced and hosted by Brian Hunter, executive produced by Scott Hall at PTA Productions. If you haven't already, please subscribe to The Occasional Podcast on iTunes, Google, Spotify, or wherever your favorite podcasts are downloaded.